Welcome back to the Explainer. So, behind every single complex process system on an FSPO, that's our floating production, storage, and offloading vessel, there is just this massive, incredibly intricate network of pipes, pumps, and valves. And they're working tirelessly, mostly out of sight. Well, today, we're bringing those hidden networks right to the surface. We're going to explore both the marine piping systems, the ones that literally keep the vessels safe and afloat, and the utility systems that support the massive oil and gas process plant up on the deck. It's a huge topic, so let's get into it. Okay, let's dive into this. First, we'll establish the concept of the vessel's circulatory system. Then, we'll look at the marine systems that keep it afloat, followed by the utility systems that support the actual production. After that, we'll examine the strict codes governing all this process piping, and finally wrap it up with a summary and our next steps.
Section 1. The vessel's circulatory system, the veins and arteries.
Let's kick things off with a pretty crucial question. What actually keeps a massive FSPO safe, stable, and producing oil day in and day out? I mean, think about it. You've got up to 2 million barrels of oil on board high-pressure gas, all sitting in a constantly moving, unpredictable ocean environment. It is a constant, incredibly high-stakes operating reality. And the answer to how it survives? It all lies in the engineering of its internal pipelines. Think of this piping network as the vessel's veins and arteries. If we use that anatomical metaphor, the marine piping systems are the vessel's core life support and survival systems. They're the heartbeat that keeps the ship from sinking or overheating. The utility piping systems, on the other hand, well, they're the muscles. They provide the absolute crucial support needed to keep that incredibly complex oil and gas processing plant functioning smoothly. Section 2. Marine systems keep it afloat. Sea chests, cooling, and bilges. And this brilliantly illustrates the main seawater cooling system blueprint. The machinery spaces on an FPSO generate an immense amount of heat, and this system right here is how the vessel breathes. Seawater is taken in through large sea chests located well below the waterline. It's filtered through strainers and then pushed by main pump trains to heat exchangers all throughout the process plant, the machinery spaces, and even the accommodation systems. And to ensure total, unbroken reliability, this system is built with at least 2 independent sea chest systems and 2 main pump trains. If one fails, no problem. The other immediately takes the load. Now, moving from cooling to flooding prevention, we have the bilge system. You can see the motif of extreme redundancy right here in the bilge mainline connecting all the compartments. But hull safety isn't just about water. It's also about strict separation. Fuel and lubricating oil storage requires total segregation from the engine room. Bulk fuel is separated by cofferdams, and absolutely no low flashpoint fuel, meaning anything with a flashpoint below 60 degrees Celsius, is allowed in the machinery spaces beyond a single small day tank. So the logic of this bilge system flows in 4 very distinct steps. First up, water collects in the bilge wells, which are at the very lowest parts of every single compartment. Second, the bilge mainline connects all of these wells together. Third, powerful bilge pumps pull this liquid out. And fourth, and this is key for environmental protection, because this water often contains oil leaking from machinery, it isn't just dumped straight into the ocean. Instead, it's sent to a bilge holding tank and passed through an oily water separator to ensure that strictly clean water is discharged overboard. In marine engineering, you live and die by the rule of redundancy. The classification societies legally mandated. It's exactly why we have dual sea chests and dual main pumps. But here's the absolute most critical thing you need to take away from this. Each machinery space must also have a direct suction connection to the emergency fire pump. That means in a severe catastrophic flooding emergency, the absolute largest seawater pump on the ship can be instantly repurposed to pump the bilges and keep the FPSO afloat. Section 3. Utility System Support Production. Firewater, drains, and gases. Now, what's really interesting about this slide is the physical firewater pipework. The active firefighting system centers around a massive ring main that literally circles the entire perimeter of the vessel's main deck. This configuration ensures that high-pressure water can be delivered to fire hydrants, deluge systems, and foam monitors absolutely anywhere on the ship at a moment's notice. The material used for this crucial firewater ring main is called Cunifer. It's a highly specialized 9010 copper-nickel alloy. Now, why does this matter? Well, because seawater is incredibly corrosive and it promotes marine growth, but Cunifer resists both seawater corrosion and biofouling naturally. It requires almost zero maintenance, it needs no internal protective coating whatsoever, and it has a service life measured in decades. Plus, because it's configured as a continuous ring main with isolation valves, high-pressure firewater can reach any point on the vessel, even if an explosion completely destroys one entire section of the pipe. Next up, we have the drain systems, and they are strictly segregated for a very, very good reason. Open hazardous drains collect hydrocarbon spills from process areas and route them directly to slop tanks. Closed hazardous drains handle pressurized equipment drains under a gas blanket inside a closed drum. Meanwhile, non-hazardous drains just collect clean rainwater or accommodation wash water for a direct overboard discharge. Accidentally mixing these streams, that would create a highly dangerous, uncontrollable contamination pathway, allowing explosive gases to migrate straight into safe areas. And that is exactly why they are entirely physically separated.
The utility systems also include some pretty vital compressed gases. Compressed air provides the pneumatic muscle for operating control valves and the absolutely critical emergency shutdown, or ESD valves. And the instrument air is strictly dry to prevent any moisture from condensing and blocking the lines. We also use nitrogen, which is generated right on board using membrane separation units. This provides an inert, non-explosive blanket gas for chemical tanks and a safe purge gas for clearing out lines before any maintenance happens.
Section 4. Strict codes for process piping, design, construction, and survival.
So, the crucial point is that every single piece of process piping on an FSO is legally bound to the ANSI/ASME B31.3 process piping code. This isn't just a best practice or a polite suggestion, it's a rigorous standard specifying exactly what materials can be used, exactly how thick the walls must be to handle internal pressures, the allowable structural stresses, and the mandatory inspection requirements.
Engineers use a piping class selection guide to strictly dictate the build. Piping classes range from Class 150 all the way up to Class 2500 in ANSI pressure ratings. For any given fluid service on the FPSO, this class selection dictates the exact compatible pipe sizes, the materials, the flanges, fittings, and valves, based on the maximum operating pressure, the temperature, and what exact fluid is flowing through it. It's a giant, perfectly calculated puzzle. And the stakes here are incredibly high, especially when you're dealing with sour service. If a pipe is carrying fluids containing hydrogen sulfide, it absolutely must comply with NACE standard MR0175. This specifies maximum hardness limits for steel in these environments. If you use steel that is even slightly too hard, you risk sulfide stress cracking. This is hydrogen embrittlement that causes sudden, catastrophic brittle pipe failure. It gives absolutely zero warning before it shatters. These warning-sounding engineering standards are, quite literally, written in blood to prevent disaster. Because the risks are so immense, the construction and inspection rules have zero tolerance. All pressure-containing welds in high-pressure or hazardous surfaces must be 100% examined by radiographic or ultrasonic testing. You cannot just guess that a weld is good. Strict welding procedure specifications must be in place, and every single welder must be individually qualified by rigorous testing before any production welding even begins on the vessel. Let's move to and see how this builds into our summary. Section 5. Summary and next steps, wrapping up Module 7. To quickly summarize our key takeaways for today, we saw how the Cunifer Firewater Ring main provides a highly resilient, corrosion-resistant, and long-life firewater supply. We learned that the build system requires total redundancy, including emergency suctions in all machinery spaces to prevent sinking. We saw that the ANSI/ASME B31.3 code governs all process piping design across the board. We understood exactly why sour service requires strict NACE hardness limits to prevent catastrophic sulfide stress cracking. And finally, we learned why drain systems must be strictly segregated into hazardous and non-hazardous streams to avoid any deadly cross-contamination. Which leaves us with one final, very provocative question. With all these redundant systems, incredibly robust materials, and strict codes designed to survive almost anything, what happens when things still go wrong? In Module 8, we are going to dive straight into the brain of the operation, the safety systems, emergency shutdown protocols, machinery protection, and the rapid response networks that take over during a crisis. It's fascinating stuff, so make sure to subscribe so you don't miss the next explainer. Thanks for joining me today, and keep learning.